Today we will be seeing about the flexibility matrix method. Okay, now we know that del times P equal to del minus del L. So here this delta is the flexibility matrix and P is the load matrix. Del is the displacement at coordinate due to released structure, and del L is the deflection due to the loading. Okay, so del is the displacement at I due to load at J, and P is the loading or moment. We know that this delta I is the deflection in released structure, and del L is the deflection due to given loading. So we will solve a simple example so that we will understand the concept. Here you see that the beam is given. This beam is ABC. Okay, here this is a continuous beam with two spans and fixed support at point A and roller supports at point C and point B and point C. Now it is subjected to UDL of 60 kN, and at this location 10 kN is acting at the center of the beam, center of the span. Now we have to determine the degree of static indeterminacy. Degree of static indeterminacy equal to 3m plus or minus 3j. So number of members here, this is one member, this is the another member. So you substitute member as 2, and reactions, fixed end you have 3 reactions, roller support you have 1 reaction, another roller support 1 reaction. So total number of reactions is equal to 5. Now joints, number of joints 1, 2 and 3. Substituting all the values, you get degree of static indeterminacy equal to 2. You understand? Now here we have released structure. Now this is the released structure where you have released the moment at this location, and at this location you apply a moment of magnitude 1 kN. So this location you choose this as redundant released structure. Here moment is chosen as the redundant, and at this location also moment is chosen as the redundant. Now here you can see that at this location you can see that we have chosen the redundance in this manner, and we will proceed further to solve the beam by flexibility matrix method. Now let us take the beam AB. So beam AB is taken here. Here it is subjected to a load of 60 kN per meter. So here the bending moment diagram is like this. You get here, this is WL square by 8 equal to 60 into 4 square divided by 8. Okay, so that is equal to 120 kN meter. This is for the span AB. So this is A and this is B. For the span BC, this is BC. Here you have a load which is nothing but 100 kilonewton, and it is at a distance 1.5 meter and 1.5 meter, that is known to us. Now here you can see that this is W by 2, this is W by 2. The reactions are symmetric, the load is symmetric, because of that the reactions we get W by 2. And the bending moment diagram is WL by 4, because W by 2 into this is L by 2, this is L by 2. So this is WL by 4, which is equal to 100 into 3 by 4. So that gives us 75 kilonewton meter. You understand? Now the conjugate beam is constructed for the released structure. So what is the released structure? Here you can see that we have two beams which are released structure. So let us name it as A, B dash, B double dash and C dash. So here you apply the bending moment diagram as the loading. So this is the loading here, and here you apply this as the loading. So for this loading we have to calculate the flexibility matrices. So how to do that? So here we know that it is 120 by EI, and for the another span it is here 75 by EI. Okay, now this is 1, this is 2, and this is A, B dash, B double dash and C dash. Okay, now theta 1L equal to shear in conjugate beam at A dash. Let us take it as A dash. Now what is the shear in A dash? It is nothing but equal to RA dash. So to find out the RA dash, summation of moment at B dash equal to 0. So RA dash into, this is 4 meter, this is 3 meter. Okay, so RA dash into 4 equal to, this is applied as the loading. So loading here, the total loading is 2 by 3 into 120 by EA. Loading is known to us. This multiplied by 4 is the loading, multiplied by the centroidal distance here is from this point to this point, it is 4 by 2. So solving all this, you get here RA dash equal to 160 divided by EA. So similarly we have to calculate for the next portion. So next portion we will take here now this is 2, this is 1. So this is RA dash, here RB dash, RB double dash and RC dash. Now theta 2L for the original beam equal to shear at point B dash plus shear at point B double dash. Now first let us calculate what is RP dash. So for that, take the beam AB dash, this is B double dash, C dash. So take the beam AB dash. Now this is your RA dash, this is RB dash, and here this is applied as loading. The loading is 120 divided by EA. Now RB dash equal to total loading, this is 4, total loading minus RA dash equal to 2 by 3 into 120 by EI into 4 minus, we have already calculated RA dash. So RA dash is 160 by EI. So this gives us here RB dash equal to 160 by EI. So since the loading is symmetrical, RA dash is equal to RP dash. You are getting 160 by EI. Then we have to calculate for RB dash. So for calculating RB dash, you take this portion. So for this portion, you know that this is 75 by EI. We are interested in RB double dash. This is RC dash. So RB double dash into L2 equal to half into 75 by EI into L2 into L2 by 2, where L2 is nothing but this L2 is 3 meters, this is 4 meters. Okay, so from this we get here on substitution and calculation, finally we get RB double dash is equal to, here it is RB double dash is equal to 75 into L2 is 3 divided by 4 EI. So that will give us here 75 into 3 by 4, that is equal to 216.25 by EI. Okay, now this is over. We have here theta 2 1 equal to RB double dash plus RB dash. Now we will find theta matrix. So whatever we have calculated is for the loading. So theta to L. Oh, now we will find theta matrix. For that you choose the beam here. Apply a load of MA equal to 1. So here you will get the loading diagram, bending moment diagram like this for the released structure. This is 1, this is 2, this is 1, this is 2. Now here theta 11 equal to shear at A. So this is A, this is B and this is C. So you take moment about B equal to 0 for the span AB. So for that you get RA into this is 4. RA into 4 equal to half into 1 by EI. This is 1 by EI. This is 1 by EI into 4 into 2 by 3 times 4, because centroid is here. So you are taking moment about this point. So from this point the centroid is located here. From here to here it is 2 by 3 into 4, and this is the length of AB is 4. Also you have here RA into 4 equal to half into, so RA into 4, you are taking moment about this point. So this you are getting. From this you get RA equal to 4 by 3 EI. Okay. Now this is equal to theta 11. Now we have to calculate what is theta 21. So 21 means at this location, because of this loading, what is the theta? Now actually you are not applying loading, you are applying moment. So in this case it may be seen that the moment here, because of this moment you have theta here and you have theta here. So at this location, theta 11 means rotation at point 1 due to moment at point 1. At this location, it is theta 21. Rotation at point 2 due to moment at point 1. This is rotation at point 2 due to moment at point 1. So this is what we have. So to find this, we need what is RB. So RB or RB dash, as we consider, RB dash is equal to half into 1 by EI into 4 minus RA. So if you substitute all the values, you get here theta 21 equal to 2 by 3 EI. So this is, so how do you get this RB dash? You take this span AB dash and here you subtract this RA value from the whole loading. So if you do that, you get here theta 11 as 4 by 3 EI and theta 21 as 2 by 3 EI. So next is finding out the theta 12 and theta 22. So let us consider the beam here. We are applying moment at this location. In this location we apply moment. So here you have the conjugate beam like this. In this fashion you get the conjugate beam, and the magnitude of the bending moment is nothing but 1 by EI. Here also 1 by EI. Now this is 2. So here you have theta 12 and at this location theta 22. Now theta 12 equal to, this is A, this is B dash, this is B double dash, this is C dash. Theta 12 equal to RA dash equal to R1. So you take moment at B dash equal to 0. So RA dash into, this is 4, this is 3. 4 equal to half into 1 by EI into 4 into, this centroidal distance is 1 by 3 into 4. Okay. On solving this, you get RA dash equal to 2 by 3 EI equal to theta 12. What is theta 12? Rotation at point 1 due to moment applied at point 2. So 1 stands for the location and 2 stands for the application of moment or loading. Now we will find theta 22. Theta 12 is found as 2 by 3 EI. For theta 22 we have RB dash plus RB double dash. Okay, so take the beam A dash B dash. First you take beam A dash B dash. A dash B dash is taken. Summation of moment at A dash equal to 0. So RB dash into 4 equal to half into 1 by EI into 4 is the loading. Okay. Then you multiply it by the centroid. You are taking moment about this location. So from here to here it is 2 by 3 into 4. So 2 by 3 into 4. This gives us RB dash equal to 4 by 3 EI. Then you take the next span. You take this span B double dash C dash. This is 1 by EI. Summation of moment at C dash equal to 0. So RB double dash into, this is 3 meters into 3 equal to half into 1 by EI into 3 into this centroidal distance. This will be equal to 2 by 3 into the centroidal distance is 2 by 3 into 3. So you cancel all these things, then finally you get RB double dash equal to 1 by EI. Now theta 22 equal to RB dash plus RB double dash equal to 1 by EI plus we had 4 by 3 EI. You understand? So from this we get theta 22 equal to 7 by 3 EI. This is theta 22. So we have found out theta 22. Theta 12 equal to theta 21. Okay. Now final displacements are del 1 equal to 0, del 2 equal to 0. There is no sinking of support, so you can choose del 1 equal to 0 and del 2 equal to 0. Now we know that del matrix into P matrix equal to del minus del L, where del is the final displacements and del L is the displacement due to the loading at the released structure. Okay. Now here del and P are related. No, but actually what we have is we have relation between theta and M. So theta 11, then theta 12, theta 21, theta 22 multiplied by M1 and M2. So you understand that here the theta is related to M and delta is related to P. If you apply loading, you get displacement. If you apply moment, you get rotations. Okay. So this is equal to delta matrix is 0, 0. There is no sinking of supports minus we already found del L. So del 1L is 160 by EI and del 2L is 216.5 by EI. So this we have already. Now substituting all the values, here we have 4 by 3 EI, 2 by 3 EI, 2 by 3 EI, then 7 by 3 EI, multiplied by M1, M2 equal to 0, 0 minus 160 by EI, 216.5 by EI. You understand? So if you solve this, you will get M1 and M2. So what is M1 and M2? You are getting here minus 85.87 and minus 68.25. These are the redundant moments that we have solved. So we have solved the indeterminate structure and we have found out the moments. Next is drawing moment diagram. You understand here that this is the beam and here this is A, B and C. At this location you have 85.87 and here you have 68.25. So if you draw the bending moment diagram, first you draw here we have WL square by 8 and we have WL by 4. This is 120, this is 75. Then you have here 68.25. At this location you have 85.87. You join them. Then you have bending moment diagram like this. Okay. So this is how we solve the beam, indeterminate beam by using flexibility matrix method. thanks a lot for watching. If you have any doubts, you mention in the comment section. You please subscribe the channel. Thanks.